billionth of a second, the cosmos burst into existence. Not a blast into empty space, but space itself stretching into being, converting pure energy into the first particles that ever existed. But for every billion particles of matter created, a billion antimatter counterparts should have annihilated them entirely. Nothing should be here. The reason anything survived traces back to the universe's very first moments. Between 10 to the minus 36 and 10 to the minus 32 seconds after the beginning, the fabric of space stretched everywhere at once, expanding by a factor of 10 to the 26 in linear size. Because this process occurred uniformly at every point, the universe emerged with no physical center and no outer edge. On December 6, 1979, physicist Alan Guth calculated the governing equations for this rapid inflation. His mathematics revealed that this sudden, colossal stretch of the vacuum would instantly freeze subatomic quantum fluctuations, magnifying them into macroscopic ripples across the cosmos. These primordial density variations became the primary gravitational templates that eventually gathered cooling matter to form the first stars, galaxies, and cosmic structures. As the metric expansion slowed, the uniform energy of the vacuum began to decay. This transition, known as reheating, flooded the cosmos with an intense uniform heat, transforming a cold, empty void into a dense thermal bath. Here, Einstein's famous equation E equals mc squared acted as the direct physical bridge between abstract energy and tangible matter. Pure radiation crystallized into the earliest building blocks of reality. Within a tiny fraction of a second, the temperature of the newborn universe reached roughly 10 to the 15th Kelvin. Through this rapid thermalization, the very first physical particles, quarks, gluons, and leptons, condensed into existence. They formed a searing, high-energy soup that packed every corner of the expanding cosmos. At 1 microsecond, this soup settled into a dense, charged quark-gluon plasma. The newborn universe was not an empty, dark void, but an opaque, white-hot fog of subatomic particles. Free-roaming electrons and quarks constantly deflected photons, trapping light in a relentless, random walk. This extreme scattering meant a single photon could only travel centimeters before colliding, rendering the entire cosmos completely impenetrable. The radiation here was a temperature-linked energy distribution peaking at over 1 trillion Kelvin, a glowing field destined to slowly stretch and redshift into the faint cosmic microwave background. But inside this searing plasma, a lethal symmetry threatened to erase all future structures. With matter and antimatter poised to annihilate each other completely, only one question remained. Why did anything survive? A tiny mismatch in the cosmic math saved the universe from total self-destruction. In those early moments, equal amounts of matter and antimatter should have collided and completely annihilated, leaving behind nothing but an empty bath of pure light. Instead, for every 10 billion particles of antimatter, the universe produced 10 billion and 1 particles of matter. This minuscule asymmetry, a survival rate of just 1 in 10 billion, left behind the leftover material that eventually built every star, planet, and living thing. The creation of this tiny surplus is known as baryogenesis, the physical process that generated more matter than antimatter in the early cosmos. In 1967, physicist Andrei Sakharov outlined the 3 physical rules required to favor matter over its mirror image, now known as the Sakharov conditions. He realized that the young universe had to violate certain fundamental symmetries, drop out of thermal balance, and allow reactions that favored matter over its opposite. The first proof that nature actually behaves this way came from Brookhaven National Laboratory in 1964. Physicists James Cronin and Val Fitch set up a 57-foot beamline to study subatomic particles called neutral kaons. They discovered that these particles and their antimatter counterparts did not decay identically, proving that physical laws treat matter and antimatter differently. Cronin later called the breakthrough the greatest pleasure of encountering an unexpected discovery. During this early epoch, the underlying physics of the universe transformed. At about 10 to the minus 12 seconds, a transition occurred called electroweak symmetry breaking, the moment when the force of electromagnetism split away from the weak nuclear force. This split activated the Higgs field, an invisible grid extending across the entire cosmos. As particles moved through this field, they experienced a physical drag that gave them mass, transforming massless energy into the stable, physical building blocks of reality. For nearly 380,000 years, the infant cosmos remained trapped in its own glowing fog. Although stable matter existed, the universe was entirely opaque. Innumerable free electrons surged through space, acting as an inescapable barrier to any moving radiation. Every newborn photon could only travel a few centimeters before colliding with a charged particle, bouncing endlessly in a tight, claustrophobic random walk. The early universe was intensely hot, but completely blind. Then, as the steady expansion of space stretched the cosmos, the overall temperature cooled to approximately 3,000 Kelvin. At this precise threshold, the thermal energy of the plasma subsided enough for the electromagnetic force to take its next step. Wandering electrons slowed down, captured by the pull of waiting protons. For the first time in cosmic history, these particles bound together to form stable, neutral hydrogen and helium atoms. This widespread atomic pairing is known as recombination. By sweeping the chaotic sea of free-floating electrons into orderly atomic orbits, recombination instantly cleared the cosmic highway. The dense, scattering fog that had choked the young universe simply dissolved. With the barrier gone, light was at last set free. This physical release, called photon decoupling, allowed the primordial radiation to escape the matter that had imprisoned it for millennia. No longer deflected or absorbed, these photons began to free stream, traveling unimpeded through the vast, newly opened expanse of space. The ancient cosmic darkness was broken, replaced by a soft orange-red glow that expanded uniformly in every direction. These freed photons would travel for over 13 billion years across the expanding void, destined to cool and stretch into the faint microwave whisper that still fills our sky today. The hidden universe had at last become transparent. In 1965, on Crawford Hill in New Jersey, radio astronomers Arno Penzias and Robert Wilson were calibrating a sensitive 20-foot horn reflector antenna for Bell Laboratories. No matter where they pointed the instrument, they detected a persistent isotropic background hiss. It remained entirely uniform, showing no seasonal changes, atmospheric alignment, or directional variance. After painstakingly eliminating every possible local source, even evicting nesting pigeons, and scrubbing their droppings from the metal horn, the unexplained excess temperature remained at over 3 Kelvin. Just a few miles away, at Princeton University, a theoretical team led by Robert Dicke realized the Bell Labs engineers had accidentally detected the cosmic microwave background. This was the long-sought relic radiation from the hot early universe, stretched by billions of years of cosmic expansion into the microwave band. This discovery transformed cosmology from speculation into an observational science, initiating a continuous chain of space-based verification. In 1989, NASA's Cosmic Background Explorer, or COBE, measured the radiation with extreme precision, confirming it matched a perfect blackbody spectrum, while mapping the first microscopic temperature fluctuations across the sky. Later, the WMAP and Planck satellites refined this cosmic map, to exquisite resolution, revealing the primordial density seeds that eventually grew into stars and galaxies. Today, this ancient afterglow has cooled to exactly 2.73 Kelvin, serving as a pristine fossil record of the infant universe. Every atom in your body traces back to that initial spark. Today, when we look deep into space, we are staring at our own oldest portrait. The cosmos continues to expand, carrying us into an uncharted future. What do you think lies ahead? Share your thoughts below.